Right, so here's a video on week 8 notes, and everything in this, generally speaking, has to do with molecular bonds and polarity. So if you look at this diagram here, what students should be able to do is determine if they're polar or they're nonpolar. And nonpolar means it will dissolve in water, and nonpolar is wouldn't. And you can tell based on, considering that the outside elements are all the same here, so if they weren't the same, this rule wouldn't apply. But in this sense here, I think it's important to be able to see if something is polar or nonpolar. The way you can look at it is if the middle red atom in this case would move, it would most likely be polar in a tug-of-war contest. So if the outside atoms were pulling or pushing at the same amount and it was equal and opposite, it would be nonpolar. So let's just look at the ones. So first of all these with no lone pairs, all of those angles are equidistant to each other, or at least equal and opposite. So all those are going to be nonpolar. Then we look at the ones that have just a lone pair, and if that was the case, the green one, if they're pushing or pulling, in a sense it would make that molecule polar. So with this bat one, T-shaped, and this T-shaped. And so look at those closely and see that, well, everything is equal and opposite. So, or something is not equal and opposite. So the ones that I've circled that are polar, there's something not equal and opposite. Compared to the ones in red that I'm circling, everything is equal and opposite. Those would be nonpolar. So the lone pairs are equal and opposite, like look at that square planar one, or that linear one at the bottom right. Notice how those electrons are equal and opposite, and the bonds are equal and opposite. Here's just a reminder that fluorine has the highest electronegativity. Francium has the lowest. So fluorine would be the strongest in a tug of war when pulling electrons. And then noble gases have no electronegativity. Lots of students have gotten that wrong. Noble gases do not want electrons. They have full electrons and therefore would not pull on shared electrons if they were sharing them, and most likely they won't be. Here's an example of a nonpolar compound. So carbon dioxide, if we drew the Lewis structure like this would be completely symmetrical. And also carbon dioxide is what they put in soda to carbonate it. And soda, with those gas molecules in it, vibrate more on our tongue, so it makes soda taste better. So they carbonate it, but slowly that carbonation leaves because carbon dioxide does not dissolve in water, compared to oxygen, where that dipole is being pulled towards that oxygen there. And so we have a negative charge over here and a positive charge over by the hydrogens. So these go back to week 7 notes. We do a lot of these in week 7, but just know that if something is nonpolar, it will dissolve in oil or other nonpolars. And if it's polar, it would dissolve in water. And we'll talk the rest about all this stuff here in the slides at the end. So I'm just going to mention the 4 types of intermolecular forces you're going to hear about. First, you're going to hear about dispersion, which occur between all molecules. Dipole, which occurs between just polar. Hydrogen bonds, which occur between polar that have a hydrogen and a NOF, and the hydrogen is not connected to a carbon. And then ion dipole is between an ion and a polar compound. So it has to be a polar compound. And these get stronger as you go down. But keep in mind that dispersion forces can be, there's a ton of them, stronger than the rest. But for now, just know dispersion is the weakest. Dipole, hydrogen bond, ion dipole. So what a dispersion force is, an electron of a different compound is attracted to a proton of another compound. So if this guy is the electron, and the girl is the proton, this other girl is the proton. So it's not like this guy's leaving his girlfriend, even though she might dump him now, but that wouldn't help you learn anything. So let's pretend she's not going to dump him now. Maybe she should, but, you know, all right, I'll show you what I mean. So I'll show you what I mean here. You know that protons will repel, electrons will repel, protons and electrons will attract. So if we have a helium atom with 2 protons and 2 electrons, there is a brief dipole moment where these electrons are attracted to those protons. And a big part of that reason is because these electrons are not in the way. So if electrons repel, you know that if they were in the way, maybe that attraction wouldn't happen, or at least as much. So something like this, if we have helium again, these electrons can't really see that proton, or at least are repelling to the other electrons. So therefore that attraction doesn't take place. So even helium, which is very stable and does not want to be attracted to other helium atoms, there is a brief moment of attraction, which is known as a dispersion force. Now we know as we go down the periodic table, dispersion forces increase. And now let's just pretend these are all nonpolar compounds. Let's say if we got A, B, B, or something like that, meaning they're symmetrical, meaning they don't dissolve in water, and all you have is dispersion forces. So if something is nonpolar, it only has dispersion. And so as you go down the periodic table, dispersion forces increase because there's more electrons, and electrons are further away from the protons. So you know as we go down the periodic table, radius increases, and the amount of electrons increases because the amount of shells increase, or the radius. Forget what I just said there. But as you go down the periodic table, the radius increases, therefore the protons and electrons are further away from each other, and there's also more electrons for that moment of dipole to occur. However, as we go across the periodic table, there's a smaller radius, even though there's more electrons, but dispersion forces decrease because the electrons are closer to the protons. And then if they're carbon-based, you can't, the reason why I wrote this notes in, it didn't occur to me at the time, but when I was in lecture, but like why did I write this in these notes last year? And if it's just carbon and hydrogen, you can't really look at where it is on the periodic table. You would not be able to look. So it's just based on mass. So these here simply are both, all these compounds here are nonpolar. So let's look at that third one. If I were to draw the Lewis structure, the dots will go around the Cl. And then if I were to draw this one, you know, they're both symmetrical, they're both nonpolar. But chlorine is a larger atom because it's lower on the periodic table. It also has more electrons, and therefore SiF4 will have greater dispersion forces. And the greater the dispersion forces, the higher the boiling point. So up dispersion, up boiling point, and so does melting point. So if you think about it, something that has a high melting point will have a high boiling point as well. So if you wanted to boil an aluminum can, you have to first think, well, is it hard to melt it? Yeah. Is it hard to boil it? Yeah. Like nothing's going to be like, oh, the second I melt it, it boils. So if one goes up, the other goes up as well. And the reason again for that is the radius is larger, meaning the electrons are further away from the protons, plus there are more electrons. And that has to do with the fact that if something wants to evaporate or boil, so just GeF4, if there's an attraction between the two, like right here, that has to break for it to break further apart or for it to evaporate. Now here's another example. As we go down, we know it gets larger, so these are somewhat obvious at the beginning, but at the end here we have one long carbon. We have two carbon compounds. The first one is like written like this. The second one, hopefully I'll be able to fit on here, CH3, CH2, saying that there's three CH2s in the middle. Top one is propane, the bottom one is 1, 2, 3, 4, 5 pentane. You don't have to know those names, but you will if you take more chemistry. And because there's just more total electrons in there, there's going to be more chances of dispersion forces. So you can correlate the larger or the higher molar mass compound with more dispersion forces and therefore a higher boiling point. Now, here are just some examples of polar versus nonpolar. So I drew the compounds just for time's sake, and if they're symmetrical and there's an even poling in all the directions, you know it is nonpolar. That CO2, very nonpolar. That HI is polar. CCl4, nonpolar. Now, when it comes to the active, close to the negative side, if electrons are being pulled in that direction, that's negative, that's positive. So like on your last test that a lot of students got wrong, if we looked at this, I don't know, at a molecular level, that iodine would be pulling those electrons more. Electrons are negative, so therefore there'll be a negative there and a positive there. Same thing here with this NH3. If we were to draw the Lewis structures, nitrogen has a higher electronegativity than hydrogen. So the electrons would be being pulled towards the nitrogen, because again, electrons are negative, and the opposite sides would be positive. Therefore, the atom closest to the negative side will be the nitrogen. One more polar one here, HCN. It's a good Lewis structure to sort of practice with. Nitrogen has the highest electronegativity. So like if you don't need the chart, or in the chart I don't even want you to use, but like here, that's like that number, that electronegativity is like how good it is at tug of war. Like nitrogen, just like enough or fun, depending on if you had enough of this or you find this fun. Those are like the best tug of war players. Like if you're picking a team in gym class and you know you had to pick, like you're the captain, you would pick those people first. I think you should pick some of the other people first, because those people always get picked first and the other people have their feelings hurt. So I think you should be a nice person and pick the other people first. So pick francium first. But that's like in life. In this situation, you want to pick those elements first to win. And so the electrons are being pulled that way. Therefore, that nitrogen is going to be the negative side. And that's why something like this would happen. HCl, if we were to draw HCl, we'll know that is a polar compound. Chlorine is very close to fluorine, so chlorine is very good at tug of war. The electrons are going to be pulled in that direction. We have a negative side and we have a positive side. This is a dipole attraction because they're magnets, and opposite and negatives are attracted to each other. And this is what would have to be broken, that dipole-dipole interaction or dispersion force interaction or hydrogen bond interaction is what would have to be broken for it to melt or evaporate. So again, if we were to draw another one, so I picked examples like before, HI, I am actually just going to pick, whatever, I'll just do it. So iodine is negative. I mean, it's just like the last one. So there's that dispersion force right there, dipole force. And negative and positive, if I said where's the negative, where's the positive, like that. And same with this NH3, you have that negative on that there, and then if we were to draw another one, the positive will be on this other side. I don't know, I probably want to make it more look like it's going from a hydrogen, positive there. So that dotted line here is where that dipole would be. So yeah, I must save this from class lecture. So yeah, looks good to me. All right, so H bonds occur when a polar compound has hydrogen and three certain elements. It exhibits dispersion, dipole, and H bonds. So again, we said earlier, dispersion are the weakest, dipole are stronger, hydrogen bonds are the strongest. Then if that hydrogen, though, is connected to a carbon, there isn't enough charge for this H bond to occur, meaning carbon and hydrogen have very similar abilities at tug of war. Sure, carbon would win, but hydrogen would I don't know, give the crowd something to cheer about. So therefore that hydrogen can't be connected to a carbon. So if we look at these here, we know all of them have dispersion. So like we said, even nonpolar compounds have dispersion. And since Selene is nonpolar, we stop there. We stop at dispersion. Hydrogen sulfide, H2S, gosh, I can't believe I don't remember. No, that's bent. So anyways, here, so we know then this is polar, H2S is polar, ammonia is polar, ammonia is NH3. Then does it have hydrogen bonding? So it has to contain a fun and a hydrogen, and the hydrogen's not connected to a carbon. So no hydrogen bonding for the first one. Second one, or the first one has all the hydrogens it follows neither of the rules. H2S, it doesn't have a fun in it. And H3, that does have hydrogen bonding. And that place where the hydrogen bonding will be in the same place as that dipole bond that we showed before. So I'm going to pick the next example too. So HBRO, so first off, we know these all have dispersion. Then O2, we stop at dispersion because it is nonpolar. HCl, carbon tetrabromide. So we're going to stop at dispersion. Then HCl does not. So this does not, this is dipole, this is dipole. So HCl is polar, so that's going to have dipole. HBRO is polar, so it's going to have dipole. Then HBRO is the only one that has hydrogen bonds, but I'll draw it in the next slide. HBRO. So I'm pretty sure the Lewis structure is just like this. Oxygen has the highest electronegativity. Hydrogen has the lowest. So technically this structure will be wrong. I think I said that I'm not going to mark it wrong, but I'm just going to draw it right. Here, BR 1 2 1 2 H O 1 2 3 4 5 6 18 years, same freaking dots. Okay, so because we have that negative charge, electrons are being pulled towards that oxygen, and then bromine, again, those electrons are being pulled that way, electrons are being pulled that way, so hydrogen is going to have a positive charge. That's where that H bond would occur. It's also a dipole bond, and in a sense, I guess it's dispersion, but that, forget I said that. And so here in OH, if there's an OH on things, it forms a lot of, I'm just going to write C over there, a lot of hydrogen bonds, because we have a hydrogen and a fun, and then the hydrogen from another OH will form a hydrogen bond there. So the more OHs on a compound, the stronger the intermolecular forces, the higher the boiling point, the higher the melting point, and so forth. So here, we know that if it is polar, so what is it? Oh, we're looking at hydrogen bonds. So no, that doesn't have a hydrogen and fun. Next one does have a hydrogen and fun, and a hydrogen is connected to a nitrogen. Last one, we have a hydrogen and fun, but all those hydrogens are connected to a carbon. Then if we had to draw it for water, so let's say if I go like this, what I'll probably have you do is draw a water compound showing the hydrogen bond. So that would be that hydrogen bond. It's between a fun and a hydrogen not connected to a carbon. Then another one here, like there. And really, for that one as well, we could do this. So that might be a good question. Like, what are two hydrogen bonds that I can draw on this second carbon? Or draw hydrogen on two different elements. That would be a good question. So hydrogen bonds just sort of explain some major characteristics, especially water. Water has a lot of characteristics that make it somewhat special, including that it expands when frozen. So expands when frozen. It has capillary action. Then what else? Oh, high surface tension. And so if you think about all these, it would make sense. You know, like if you have to break these hydrogen bonds, if you jump into water, you know, it's going to have a high surface tension. Then capillary action makes, you know, water has these strong hydrogen bonds. They want to stick together, but they also have like a strong magnetic property to them. Then because of hydrogen bonds, which are again strong, those tighten up and when the molecules slow down, and therefore sort of become like rigid in a sense. So that's why water freezes. So lastly, here we have the strongest of them, and that is ion dipole. That's only if a ionic bond dissolves in water. Ionic, remember, is between the left and right, or metal and non-metal, and or if not just water, but if it dissolves in any sort of polar compound. So if MgCl, ionic compound, Mg is on the left, Cl is on the right, it's an ionic compound. Mg is going to be smaller than Cl because magnesium loses 2 electrons, becomes smaller. Chlorine is larger. So that negative side on a oxygen is going to face that magnesium, and that makes sense. This is an ion, and this is a dipole, polar compound. An ion is a charged particle. Compared to this one, the hydrogen is going to be facing the negative charge ion because the hydrogen is positive. Remember, the electrons are being pulled towards the oxygen. Electrons are negative, therefore that positive charge would be facing that. So on this last slide here, I don't know if I can't erase all this. So here we're looking for the ionic compound is going to have the highest. Then in blue, C just has dispersion. All of them have dispersion. Then HCl has dipole, but it doesn't have a H bond. The next one has dipole and H bond. Last one just says dispersion. So HCl dipole or dispersion dipole. H2O2 has dispersion dipole and H bonds, and then H2 just has dispersion. That's why the order is written that way. The ionic bond has the highest melting point, and then the lowest is H2, and then H2O2 has a higher one than HCl. And said melting point again because melting point and boiling point correlate.